everybody. Hopefully everybody can hear my voice. If not, they're going to watch me point at this little sign, and hopefully we'll get on board and get the sound up and running. Alright, this is a lesson out of the Chapter 4 Study Guide for Geometry, and this is 4.7, Chapter 4, Section 7. This one has to do with properties of isosceles and equilateral triangles. So the two concepts, they're not exactly the same type of triangle. An isosceles triangle is a triangle that has two sides that are the same and the third side that's different in length. That's your isosceles. And an equilateral triangle has three sides that are all the same length. Okay, so we're going to use the properties of these types of triangles to try to solve problems. Legs are just kind of another word for sides. So in an isosceles triangle, the legs are here and here, and the base is the side of the triangle on the bottom. These are base angles on each side, and they are congruent to one another. And then finally up here, this is called the vertex angle. So, base angles theorem says that if you have two sides on an isosceles triangle that are congruent, that the angles that are across from one another, from the two sides, also known as the base angles, then also have to be congruent. We're going to use this theorem a lot in geometry this year, so hopefully you'll remember it. The converse of the base angles theorem simply says that if you have a triangle where you have two angles that match, that means that the sides opposite from those two angles would have to be congruent. So, for example, if you have this side congruent with this side on a triangle, that means that that angle and that angle would have to be congruent, according to the base angles theorem for isosceles triangles. So, here's some examples. You can see that this side and this side are marked congruent. So that means that this angle over here would have to be the same measure as that angle over there. So we can say that those two are equal. And we can solve for x by solving this equation. X equals 22. The value of y is going to be a little harder. If we substitute 22 here, 2 times 22 is 44, plus 11 is 55. So this angle right here is 55 degrees. And 3 times 22 is 66. Minus 11 would make this angle the same, 55 degrees. Well, we said they'd be the same, right? If these two sides are congruent, then those angles opposite would have to be the same measure. Absolutely. So if these two angles, if we add them together, get 110 degrees, right? These two. And if the whole triangle's angles add up to 180, then what would this one be? Well, 180 minus 55 minus 55, or 180 minus 110, however you want to think about it, would be 70, right? So that's how we know that that last angle would have to be 70 degrees. So we can set that up as a statement of truth. This angle marked as 2y is the same as 70 degrees. And if we solve that equation, we get that y is 35. The second one is an isosceles triangle, right? Two sides that are equal in measure. That means that these two angles would have to be equal. Well, we can't make an equation though with that, because you can't say 3x equals y plus 7. That's two letters in the same equation. You can't solve that equation. Well, if this is 90 degrees up here, and these two are equal to one another, and the whole thing adds up to 180, wouldn't these two together have to be 90? Because these two would be 90 and that one would be 90, then the whole thing would be 180, right? And if each of them is the same as the other one, wouldn't they each have to be half of 90? So wouldn't this have to be 45 and this have to be 45? Yeah. 45 plus 90 is 180. So that's how I figured out that each one of these corners would have to be 45 degrees. And now I can set up two equations and solve for both x and y. On example number 2, we have an equilateral triangle. And when you have all three angles or all three sides that are the same, then you also know that all three angles would also have to be the same. How do we know that? Well, up at the top of the page, they've given us some more theorems. If a triangle is equilateral, then it is also equiangular. If all three sides are the same, then all three interior angles are the same as each other. Or vice versa. If you have, here's the converse of the theorem, if you have all three angles that are the same, if the triangle is equiangular, then all three sides are the same. Then it is also equilateral. So down at the bottom of the page, back to that example. We have all three sides that are congruent. And I said that means that all three angles would have to be congruent. So if we know that angle R plus angle S plus angle T adds up to 180 degrees, but we know that each one of these represents exactly the same thing, we could just call them X. Angle X plus itself one more time adds up to 180, right? Since we know they're all the same measure. So setting it up this way is an equation that we can solve, because x plus x plus x is 3x. And solving it out, we get x equals 60 degrees. Each measure is equal to the other angles, and they're all equal to 60 degrees. Let's do number 4. This diagram, I have this angle right here and this angle right here, both with x's in their expression. So I'm thinking, it'd be nice if those were equal. Are they equal? Well, on this triangle right here, this side is marked congruent to that side. So that means the angles opposite from those sides would also have to be congruent, right? Based on the isosceles triangle base angles theorem. So Yeah, it is true. These two angles are the same. 5x minus 10 is equal to 3x plus 10. So I can find x by solving this out. Okay, how about y? Well, y, I see a y right here. It's part of the name for this corner for y. How would I figure out how much that is? Well, I would say that working with this triangle a little bit more, trying to find the actual measures of each one of these corners would be helpful. So for example, this angle right here would be 3 times 10, because we know x is 10, so it's 30, plus 10 is 40. So this angle right here is 40, which means that this angle over here would also have to be 40. So if this triangle, if I know all the interior angles add up to 180, and these two are 40, that's 80, so wouldn't this corner have to be 100? Yeah. Now across the top of this triangle, the big whole triangle, not this little one, I have this line right here, where I've just written right here that this is 100, right? Now isn't this a straight line? Goes across like that? If this side is 100, and how much would this side be? Well, we know that when we have something called a straight angle, which means it goes from one side of a straight line over to the other side, that the total is 180. So if this side is 100, then this side would have to be 80 right there, right? So this little angle right there would have to be 80 degrees. So this little triangle on the side has markings as well. It says that this side is congruent to that side. So we know that this angle over here would be congruent to that angle over there. So that means that this angle, which is 80, would have to be congruent to this angle, which is 4y. So 4y equals 80. And solving that gives us 20. All right, and then the page with some proofs on it. I'm just going to do this top one here. This top proof says that FG is congruent to FJ. So I'm going to mark those even though they haven't been marked in the diagram. It's okay as long as it's stated in the given. You can mark them. And HG, that's this segment, is congruent to IJ, that's this segment. So, what are we trying to prove? We're trying to prove that HF and IF, these two, are congruent. Okay. Well, what I see is that this large triangle is isosceles because this side and this side are congruent. So I'd be able to say that this angle right here is congruent to that angle right there based on the base angles theorem for isosceles triangles, which is actually the converse. I could use this one right here. Oops, wait, no, this one right there. Yeah, the regular base angles theorem. Then, if that angle and that angle were congruent, I would have a pair of sides that match, a pair of angles that match, and then another pair of sides that match. So if I were looking just at this triangle and this triangle right here, seems to me like I would be able to prove that they're congruent by side angle side. Once I established, not in the screen. Once I established that this triangle and this triangle were congruent by side angle side congruence theorem for triangles, then I certainly would be able to state in phase 2 that HF would have to be congruent to IF, because they would be two corresponding parts on a pair of triangles that I just said were congruent. Once you establish two triangles are congruent, then any corresponding parts must also be congruent. So here's my given. FG is congruent to FJ, and HG is congruent to IJ because that was given. I'm going to try to show that those two triangles are congruent. The way that I did that is I wanted to establish these two angles as congruent, and I knew that would work because this whole triangle right here is isosceles. So I'm going to say that angle FGH is congruent to angle FJI because of the definition. I don't know. Yeah. I could say what's the base angles theorem of isosceles triangles. So now I have a pair of sides, a pair of angles, and a pair of sides where the angles are in between the sides. So I could say that triangle FGH, that's this one over here, is congruent to triangle FJI, it's that one right here, because of the side angle side congruence theorem for triangles. So that's phase 1. Is showing that two triangles are congruent. Once you know two triangles are congruent, then any sides or any angles that are in corresponding positions would then have to be congruent. So since HF is a corresponding side with IF, and I already established on step 3 that the two triangles are congruent, then now I can say that these two parts that correspond would then also have to be congruent by the corresponding parts of congruent triangles are congruent. Phase 2.